So in this pattern, we're going to add numbers, rewrite them in a different way, and see how they connect to perfect squares. And this is just a fun pattern. Not much is needed to be said. In the first case, we can just say 1 equals 1. And that is like saying 1 times 1, or 1 squared. And then we can build this up and say, well, what if you take 1, add it to 2, and then go back down to 1? What do we get then? Well, we get 4, or 2 plus 2. So that's the same thing as 2 times 2, which is 2 squared. Okay, now what if I go 1 plus 2 plus 3 plus 2 plus 1? What's that like? Well, in that case, that's like adding 3 threes. 3 plus 3 plus 3. Or 3 times 3, or 3 squared. In the next case, we go up to 4. So 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. And what's that like adding? Well, that's like having 4 fours, or 4 times 4, or 4 squared. And then what if we build up to 5? So 1 plus 2 plus 3 plus 4 plus 5, and then back down 4 and 3 and 2 and 1. That's like adding 5 fives. 4, 5. Or 5 times 5. And we can keep going with this all the way to 1. Oh, all the way until we get, or climb all the way to 9. So 1 plus 2 plus, I'm going to try to fit this, 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4, that's a plus sign, plus 3 plus 2 plus 1. Whoa, that's like having 9 nines. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or, running out of room here, this equals 9 times 9, or 9 squared. So not only does this pattern look really cool, where 1 plus 2 plus 1 is the same as 2 plus 2, or 2 times 2, or 2 squared, or 1 plus 3 plus 2 plus 3 plus 3 plus 2. Well, I'm sorry, I was talking too fast. 1 plus 2 plus 3 plus 2 plus 1 is the same thing as 3 threes, or 3 squared, right? This works all the way across. Something interesting happening here, I think, that becomes easier to see when we mess around with the commutative property, and that's the order, right? The commutative property says we can add in any order and still get the same thing. So how come 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way to 9 and back down to 1 is the same thing as 9 nines? How do we know that? I think it's easy if we take the number and fold it. So we go 1 plus 2 plus 3 plus 4 plus 5, 6, 7. Move this down. And erase this. Sorry. So we're rewriting all this, the last sum that goes all the way to 9 in a different way. And then flip it, right? So make like a fold and a flip. So we have 8, 7, 6, 5, 4, 3, 2, 1. So what do we notice? Well, when we climb up to 9, and here's the peak, let me move this over, go all the way up to 9, and then we come back down. I just reversed that order here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back down. If we change the order a little bit, what happens to all these pairs? 1 and 8, 2 and 7. When we add all of them, all we're going to get are 9 nines. And this can be applied to all kinds of sequences. Most famously, it's applied to the idea if I add all the way up 1 plus 2 plus 3 plus 4 plus all the way up to 100. How do I do that? Well, one idea was to add, right, all the way up to 50, 1 through 50, and then think of the other half of the numbers, and 51, all the way through 100. And those pairs will all equal 101. So you have 50 pairs of 101. And this goes back to Gauss, right? And this kind of a series, the arithmetic sequence and series, which is really fun to think about. But it goes back to this fun pattern which is just to make an observation that if you add up 1 through 5 and then 4 through 1, that's the same thing as having 5 pairs of 5, right? You can see 1 and 4 is a 5. 2 and 3 is a 5, 2 and 3 and 4 and 1 is another 5, and the 5 in the middle, the peak, right? In every case, we have that peak in the middle, so it's like having 5 fives. Alright, anyway, and I hope you enjoyed.